Hindi ka makatulog po.
I'll just share my screen. Yeah, can you see my screen?
Yes.
Okay. And this. So now, today we are trying to answer the question: how do satellites communicate? And before that, I just want to talk to my friend Dhruv. Dhruv, can you hear me? Okay, Dhruv, I don't know. I'm not able to hear you. You just change your name to Dhruv, and okay, you change your name to Dhruv. Yeah. And Akshit, can you hear me? Hello, Akshit. Okay. I don't know. I'm not able to hear him. Once again, I'll try changing my settings. Second. Ikshit, can you hear me now? I'm not sure whether he can hear me, but I think Dhruv can hear me because he changed his name. Okay, I'll study class. So how do satellites communicate? Like, do any one of you know the answer? How do satellites communicate? Hello. Hello.
Hello.
Yeah, can you hear me?
Yes.
Yeah. So how do satellites communicate?
By radio signals.
Yeah.
The
So
form of radio signals.
yeah. So what happens is the data which the satellite gather from the instruments such as such as star trackers, infrared sensors, masers, all of those get converted into electrical signals, which are then transmitted using an HGA. HGA, which stands for high gain antenna, this round thingy. Yeah. And from that, it gets sent to the tracking station, and which are then sent to scientists for information gathering.
Cool. Next.
Yeah. So, okay, radio. What is radio?
A light.
A form of light, exactly. So what happened is, yeah. Can you see? Can you see the electromagnetic spectrum?
Yes.
Yeah. So this is like a band of all the existing light that is, and we can only see a small portion of it called visible light. Can you see this narrow band? Yeah,
Yes.
you can only see that much light, and there are many other lights. We have AM, shortwave, TV. TV means radio, FM, again radio, another type of radio, and then we have radar, microwave, infrared radiation, ultraviolet, X-ray, and gamma rays. So the difference between these types of light is that the wavelength of the light. Like, do you know what's wavelength? Wavelength for waves.
No.
No. So wavelength, if let's say you have a wave, and I'll just draw it and show. Let's say that you have a wave.
Yeah.
And wavelength is the distance between each consecutive rising. Like let's say the distance between here and here. That's a wavelength. So what happens is different wavelengths of light have different types of light have different wavelengths. Like for example, radio waves have very big wavelength, right? So this distance, the wavelength for radio waves is the size of Statue of Liberty. It's that big. And the wavelength for gamma rays is just the width of the atom. Okay, so this is all well and good. Okay, sorry. So what wave? Like every wave needs a medium, right? Like water waves need water, sound waves needs air, and light waves need light waves are just oscillations in the electromagnetic field. Like let's say that you have a magnet. Sorry, let's say you have a compass. You have a compass near an electric circuit. Okay, and you turn on the electric circuit, and you can see that the compass needle points towards the electric field. I mean, electrical wire. That is because moving electrical charges, such as electrons. Once again. Sorry, my sister had to go. So, what was I saying? Yeah. So what happens is moving charges create magnetic fields, and moving magnetic fields create electrical fields. So this oscillating happens, and I cannot show you because that's in 3D. An electrical field is created, moving electric charge is creates an electrical field, which creates a magnetic field, which again creates another electric field downwards, like a bit forward, which again creates a magnetic field upwards. So it just keeps on oscillating. That is light. So this is all good. But there are, okay, I'll ask you this question. Is light a wave or a particle? Is it a particle or a wave? Dhruv, do you know the answer? Ikshit? They're not responding, I don't know. Prasanna, do you know the answer? Like, what's your guess? Is it a wave or a particle?
Wave.
That is not quite correct. So because light has this weird property, right? So it's called the photoelectric effect. Photoelectric effect. Let's say that you have a metal. This is the surface of the metal, okay? And if you shine light at it, what it does is that it knocks, like the metal has atoms, right? And the electrons get knocked off. And this is only possible if light is a wave. I'm sorry, if light is a particle. So what happens is light comes, hits an electron, and knocks it off. It pushes it and frees it. And this should not be possible if light is a wave. And another fact is that light, we all know that light can travel through vacuum, right? But we all know another thing, that vacuum has nothing. And every wave needs a medium. We need a medium for a wave to oscillate, for any waves to work. But there is nothing in space. So how do light waves travel? So we don't know. Many scientists favor the wave hypothesis, while many other scientists like Newton favored the particle hypothesis. So what happened is there is another experiment which very much proves that light is a wave. Although it's not. Okay, I'll just show you the experiment. Let's say that you have a light source. So this is a light source. And we have wall. We have two walls. This wall is a screen. This wall is a screen. And this wall has two slits in it. It has two holes in it. So what do we expect? Like if light is a particle, then we expect there to be two patterns. Like this part should be illuminated and this part should be illuminated if light is a particle. But we don't see that. We see another pattern, an interference pattern, which can only be possible if, this here. Can you see? Light is a wave and it creates an interference pattern. Like this area has a lot of focus on light. This area has a lot of minimum amount of light. And this interference pattern is only possible if light is a wave. So many scientists favor the wave hypothesis. But what happened is during the turn of the 20th century, there was two very famous equations. One is E equals mc2 by Albert Einstein, and the other is E equals hf. So h is a constant called Planck's constant, and f is the frequency of light. So this equation is used to find the energy that mass have. This equation relates mass with rest energy. We don't need to go there right now. And the second equation relates it gives us a way to find the energy of a wave, because f is a frequency, which is a property of a wave. So what happened is a college student named Louis Dubreuil noticed that these two are E's. Like they are E's. They are the same thing. So when cancel them, then we get then we get mc square is equal to hf, and c square is the speed of light and h is a constant. So these two are constant, so we can cancel them, and we are left, and what we are left with is that m equals f. Matter equals frequency. That is, particles and waves are the same. So what I'm trying to tell here is that particles. So particles and waves. Sorry, light is both particle and a wave. It behaves sometimes like a wave and a particle. So what happens is waves come in discrete packets of energies called photons, and discrete packets of energy are called particles, and the energy inside is a wave. So it's like a particle inside a wave, and this is called wave particle duality. And now to the question, is light a particle or a wave? The answer is all of these. That's it. Just stop.